example 3 is our first example of graphing a polynomial function of a higher degree. So our function is f of x is equal to negative 1/4 times 3x plus 1 times x minus 4 squared. Okay, and there are several parts to the process. There's parts A through F. If I gave you something like this, I would walk you through the steps like I do on this page, so you don't have to worry about that. But the big things that we're going to have to do here, you're first going to have to find the end behavior of the polynomial, okay? And then we're going to look at the zeros and the multiplicity of each zero. And then we're going to find the y-intercept and talk about the maximum number of turning points. And then we're going to take all of that information and put it together in a graph, okay? So we are going to start here in part A and part B. Both of these parts involve finding the end behavior of this polynomial. So remember, end behavior is basically what happens at the endpoints. And to determine the end behavior, you need to know the degree and the leading coefficient of the function. Okay, so again, if the degree is even or odd, and whether the leading coefficient is positive or negative. If you look here, this polynomial is not in standard form. Okay, it is given to us in factored form. And you may look at this and say, okay, well, how do I figure out the degree and the leading coefficient? I'm probably going to have to multiply this out. And that is not the case. I am going to show you a shortcut so that you don't have to multiply this out to get what essentially you need is the leading term, because the leading term will tell you the degree and the leading coefficient. So there's a little shortcut that I will show you that will just get you the leading term, and then you can identify the degree and the leading coefficient, and then from that you can get the end behavior, okay? But I want you to know, when you get to these polynomials of higher degree, it can be a real pain to get them in factored form. So lucky for us, the book, MyMathLab, all of your polynomials will be given to you in factored form, okay? That makes your life so much easier because, like I said, it can be difficult to factor a polynomial of a higher degree. Remember, something like the quadratic formula only works on something of degree 2. There is no quadratic formula for a higher degree. You are going to need the factored form because that's going to help you find the zeros or the x-intercepts, okay? So it is great that you are being given these guys in factored form, okay? So let's talk about the little shortcut you can use so that you don't have to multiply the whole thing out so that you can get the leading term, okay? So what I'm going to do here is I'm going to kind of rewrite this for a second. I'm going to expand it as much as I can, meaning I've got a negative 1/4 out front. When you look at that quantity 3x plus 1, that is raised to the first power, okay? So I'm just going to leave it like that. But then when you look at the x minus 4, it is squared. So if I write out what that means that this is x minus 4 times x minus 4. Okay, if you square something, you're multiplying it by itself. And again, like I said, I want the leading term. If I were to multiply this guy out, which I would have to FOIL or box, and I'd have to do it multiple times, and that's a pain, which term would have the highest power of x? Okay, well, here's the little trick that you can use, okay? To get the leading term, and again, that is the piece with the highest power of x. Okay, I am going to take the number out front. Okay, so if there's a number out front, I want you to multiply it. And I'm talking about the number out front of all the parentheses, okay? And then inside the parentheses, I want you to underline everything that has an x. And if it has a number with it, you should underline that too. So in this first set of parentheses, I've got 3x, and then I've got 1x, and then I've got 1x, okay? And notice I've done this to the format where I've expanded it out like this, okay, where I rewrote the x minus 4 squared as x minus 4 times x minus 4, okay? So now that we've got all these guys underlined, again, it's the number out front of the parentheses, and then anything inside of the parentheses that has an x, and if it has a number with it, take it with it, okay? We're going to multiply these guys that I've underlined together, and that is going to give us our leading term. So our leading term is going to be negative 1/4 times 3x times x times x. Okay, so we multiply these things together. Remember, these are over 1. Okay, multiply fractions across the top and across the bottom. This is going to give us negative 3. X times x times x is x cubed over, the coefficient will be 4 times 1 times 1. So it'll be negative 3/4 times x cubed is going to be the leading term. Okay, so that means the degree of this polynomial, the highest power of x, is going to be 3. And the leading coefficient, the number in front of the highest power of x, is going to be the negative 3/4. Okay, so you can see here, this is going to help us in part B, where we are looking for the end behavior. For end behavior, you need the degree, whether it's even or odd, and you also need the sign of the leading coefficient. Okay, so based on our results of part A, we know we have an odd degree and a negative leading coefficient. Okay, and so from that, so I don't know, what all you have done, but I don't typically memorize the rules. Okay, I just say, okay, I've got an odd degree and a negative leading coefficient. So the thing that's most familiar to me that does that is negative x cubed, and I know that negative x cubed looks like this. And so we know that the polynomial that we're ultimately going to graph out in part F is going to behave like this at the endpoints. So it's going to rise to the left and it's going to fall to the right. Okay, but you are asked to write this out in mathy language. Okay, so again, just kind of follow the cues here. If your x values are approaching negative infinity, so if your x values are getting more and more negative, their associated y values are getting more and more positive. So as x approaches negative infinity, y would approach positive infinity. And then on the flip side, if your x values are approaching positive infinity, so they're getting more and more positive, the associated y values are getting more and more negative. So as x approaches positive infinity, y would approach negative infinity. So that's how you can fill this out mathematically, okay? But again, in everyday language, when you draw this picture in part F, you want the left side to rise and the right side to fall, okay? All right, so that's the end behavior, okay? All right, in part C, okay, it says to list each real zero. So let me stop you right there, okay? Notice that that word real is underlined. Later in chapter 5, it starts getting into the opposite of real. The opposite of real is imaginary. So you can have imaginary zeros or you can have real zeros, okay? So the best example I can give you of an imaginary zero is, remember when we were doing in section 4.3, we were doing quadratic functions and we were graphing parabolas and we had to solve for the x-intercepts, and some of them we would plug the a, b, and the c into the quadratic formula and we would simplify and you ended up with a negative under the square root, and we concluded, that that meant that there were no x-intercepts for that graph, okay? Well, that's true, okay? When you graphed your parabola, there were no physical x-intercepts. But really what was going on, there were zeros, but they were just imaginary, okay? Imaginary zeros or imaginary x-intercepts do not show up on the picture, okay? So you can either have imaginary zeros or you can have real zeros, okay? For right now, we're going to be looking at real zeros. So if you had a polynomial and you ended up with an imaginary number, imaginary just means negative under a square root. Okay, you wouldn't have to list the imaginary zeros because it's only looking for real zeros. Okay, so basically we're going to find the x-intercepts, and then once we have each one, we're going to talk about multiplicity, what that means for each one. We're going to find the multiplicity associated with each zero, and then remember, you can use the multiplicity to determine whether your graph is going to cross or touch the x-axis at each x-intercept. Okay. All right, so let's go ahead and find the real zeros, okay? So remember, think back to things we've done in the past. To find an x-intercept, which is a zero, you want to set the y value equal to 0, okay? So going back to your original function, you can either use this format. I prefer this format, okay, but either one will get you there, okay? So I'm going to set the whole thing. You're setting y equal to 0 to get your x-intercepts. And remember how you solve something by factoring. The right side is already factored for us, okay? But once you have it factored, you need to take each factor, each of the things that you're multiplying together, and you need to set it equal to 0 and solve, okay? So how many factors do I have here? Well, I've got 1, 2, 3, 4, okay? 4 things that I'm multiplying together. So I'm going to take each of those factors and set them equal to 0 and solve, okay? So I'm going to go over here. I'm going to set negative 1/4 equal to 0, okay? That doesn't make any sense, okay? Negative 1/4 is negative 0.25. That never equals 0. So that doesn't make sense. We're going to ignore that, okay? If you have a number out front, do not set it equal to 0, okay? It doesn't make sense. Only take the factors that contain an x and set them equal to 0, okay? So let's take the 3x plus 1, set it to 0. Take the next factor, x minus 4, set it to 0. And if you notice, we have 2 factors that are x minus 4. I'm just going to go ahead and set them both equal to 0. Okay, so we're going to solve each of these guys for x. So for this first one, I'm going to get 3x is equal to negative 1, divide by 3. I get that my x-intercept is negative 1/3. Okay, so I'm going to go ahead and put that in the box. I get 1 x-intercept, or 0, of negative 1/3. Okay. And then solve these two. I'm going to get x equals 4. Okay, they are the same intercept here. Okay, so I'm only going to write it down once in my chart. Okay, usually when I give you problems like this, I'm going to give you this little chart. It's going to have 4 rows in it. That does not mean you're going to have 4 intercepts. Okay, I usually won't give you anything with more than 4 intercepts. Okay, so we only have 2 unique x-intercepts here, or zeros, so I'm going to go ahead and cross those rows out, but don't feel compelled to fill it up. Okay, so now it has come to the time to talk about what this multiplicity is. Okay, so multiplicity, basically, like I said, it is a number associated with each 0. Okay, so the best way you can think about multiplicity is this. Let me see if I can find some room to write this down. Multiplicity is the number of times you get a 0 as an x-intercept. Okay, so what I mean by that is, okay, here are my zeros, or my x-intercepts. How many times did I get them as an x-intercept or as a 0? Well, I got negative 1/3 one time. So the multiplicity is going to be 1. But for 4, I got it as a 0 twice, or an x-intercept twice. So the multiplicity is 2. Okay, so again, you can see it from the original formula. Okay, negative 1/3 came from this factor. Okay, the exponent on that factor is 1, and then x minus 4, or sorry, x equals 4, that 0 came from this factor. The exponent on it is 2. Okay, you can think of it that way, but again, I prefer expanding it out like this, setting each factor equal to 0 and seeing how many times you get it as a 0. That is what the multiplicity is. Okay, so the x-intercept negative 1/3 has a multiplicity of 1. The x-intercept 4 has a multiplicity of 2. And what does that mean in terms of the graph? Well, we said back on page 5, there are these rules you have to know for multiplicity, and here they are. Okay, if you are dealing with an odd multiplicity, the graph is going to cross the x-axis at that x-intercept. If the multiplicity is even, the graph is going to touch or bounce at that x-intercept. Okay, so for negative 1/3, okay, when you plot this point on your x-axis on the graph, there's a multiplicity. It has a multiplicity of 1, and so that this is an odd number. 1 is an odd number. Odd multiplicity means the graph is going to cross the x-axis there. Okay, the other x-intercept 4 has an even multiplicity. The multiplicity is 2. Even multiplicity means that the graph is going to touch or bounce at that x-intercept. Okay, So when we get to part F, we are going to use this chart to plot the x-intercepts and then exhibit the correct kind of behavior going on at each one. Okay? All right, so far we know two specific points on our graph. Okay, these are our x-intercepts. Now we're going to get an additional point by finding the y-intercept. So remember, to find a y-intercept, you are going to set x equal to 0. Okay, so go back up to your formula. It doesn't matter which one you use. I, again, usually use the expanded one. I'm going to set x equal to 0. So my y-intercept is going to be negative 1/4 times 3 times 0 plus 1 times 0 minus 4 times 0 minus 4. That is going to give me negative 1/4 times 1 times negative 4 times negative 4. Okay, if I multiply this all together, negative times negative is positive, times negative is negative. You can make these all fractions, multiply across the top, across the bottom. This is going to be negative 16 over 4. So your y-intercept is going to be negative 4. Okay, so my y-intercept is at the point x equals 0, y equals negative 4. Okay. All right, and then last thing before we put all the information together has to do with the maximum number of turning points. Okay, it says determine the maximum number of turning points on the graph. Remember, a turning point is a point where the graph changes from increasing to decreasing, or vice versa. You change from decreasing to increasing. In part E, you are not calculating what the turning points are. Okay, you're just deciding on a maximum number of turning points you can have. So when you put your picture together, okay, remember, you can't go crazy. You can't just be turning all the time, okay? There's a maximum number of turning points that you can have, okay? So remember the rule. The rule has to do with the degree. The maximum number of turning points is the degree minus 1, okay? We found in the part A that the degree is 3, and so the maximum number of turning points this function can have is 3 minus 1. So this is going to be a maximum of 2 turning points, okay? All right, so now we are ready to put our graph together, all the information from parts A through E, to draw a rough sketch of the parabola. Okay, you notice I've got a graph here with no scale. Okay, usually I give you the negative 10 to 10 graph, and the negative 10 to 10 grid in both directions. I didn't here because if you're dealing with a polynomial of higher degree, you can easily get to very high y values very quickly, and so you may have to adjust your y scale. I think for this one I am going to stick to a tick mark every 1 unit here, but if you do need to adjust your scale for some reason, just let me know what it is, okay? All right, so I'm going to start labeling the x-axis. So I've got 1, 2, 3, 4, I'll put a negative 1 here. I'm going to go ahead and plot my x-intercepts. So I have the first x-intercept at negative 1/3. You're just going to have to eyeball it. That's about right here. Okay. The other x-intercept is at 4. Okay. And then I can go ahead and plot my y-intercept because that's the third point that I know is on the graph. So here's your y-intercept, negative 4. Okay. And the graph has to go through these points. Okay. And it has to exhibit the correct behavior at each x-intercept, and it has to have the correct end behavior. So what we can do here is we can start connecting the dots, okay? So before we do that, remember what the end behavior is going to do, okay? This guy is going to rise to the left, okay? So we can expect it's going to do this. It's going to rise to the left, okay? And it's going to fall to the right, okay? Because that is what we had determined earlier in part B, okay? So it's going to look something like that. And remember, it has to go through these 3 points that we have designated right here, okay? Now, the other thing we need to deal with is what happens at the x-intercepts. Okay, so we know at negative 1/3 we're going to cross, and at 4 we're going to touch or bounce. Okay, so the way we can make this happen is we're going to, it should be rising to the left. Okay, but it's going to come down through this point, this x-intercept. It is going to cross there. It's going to cross and go to the y-intercept. Okay, and then it does something, we don't know what, okay, but it's going to come down, it's going to turn, it's going to go up to the 4, oops, it's going to go to the 4, and remember, the 4, it bounces or touches, so it's going to touch or bounce and then come back down to go to meet up to this part to keep going down forever, okay? So again, this is a very rough sketch, okay? We don't have, other than the 3 points we have outlined, we don't have specific points. Like up in here, we don't know specifically what is going on. But the things that I want to be looking for, I need to know the shape, okay? This is an odd degree polynomial. It has like the S shape going on for it, okay? I need to see the correct end behavior, okay? It is rising to the left. It is falling to the right. I need to see the intercepts, the x-intercept right here at -1/3, it's crossing. At 4, the other x-intercept, it's bouncing, okay? Here's the y-intercept, okay? And then the other thing I need to see, it's a smooth and continuous curve, okay? I didn't draw it without, I drew it and I didn't have to pick up my pencil. There's no sharp corners, there's no cusps. And the other thing is I tried to draw it so it had, you know, no more than 2 turning points. Let's see if I did that. I mean, it's decreasing and then it kind of changes to increasing and then back to decreasing. So I think I accomplished that. Okay, so we are just coming up with a rough sketch based on, you know, end behavior, zeros, multiplicity, turning points. Okay, all right, let's try